So in our past discussion, we looked at a number of applications of partial differential equations, and one of them we looked at in engineering is one-dimension heat equation. Now, we are going to be looking at the derivation of 1D heat equation, discussing it in details. So we are looking at derivation of the equation. Now, first of all, we are going to say that the heat conduction equation is given by, we have Uxx is equal to 1 out of c squared, then ut, or we can say del u, del 2u, del x squared is equal to 1 out of c squared, del u, del t. So from there, we need to define how we are going to solve this. So we are going to use a method of separation of variables. So this is going to be method of separation of variables, and we are talking about analytical solution. So remember, we can have two, one being analytical and another one being numerical. So numerical solution shall see it in the future. Analytical solution by method of separation of variables is what we are going to discuss right now. So now we are going to say for example, this heat distribution or heat conduction is going to be defined by two variables at a particular point x and a particular instant, that is time. So ux t is going to be also a function of x, okay, times a function of t. In other words, we are making this as a trial. This is a trial. Okay, we are making a trial that since this function is going to be defined by the position x and also the instant time t, then we can take this x to have its own function. We have a function of x that is position or distance or displacement, and then t, capital T, a function of small time t. So we are talking about the fact that if you have a metal bar whose temperatures have been fixed at the ends, so you have x is equal to 0 here, you have x is equal to L. So at any instant in time, you can have the heat, the amount of heat here different from maybe at another instant, but obviously at different positions. For example, if I said this is x1, you have x1, maybe you have x2, you have x3, maybe you have x4. So you'll find that the heat distribution at x1 is different from the one at x2, at x3, at x4. And here we are assuming that this bar is insulated, meaning we have only one flow of heat in one direction actually. Heat is not being lost to the surroundings, heat is only traveling in one direction. And therefore, if it is able to flow, for example, we are assuming like a heat flowing in a pipe, and there is nothing like escape along the journey from x is equal to 0 to x is equal to L. So let's take our trial solution and we do something about it. So we have u is equal to x times t, and this is a simplified model. So now, if we have u is equal to xt, remember we can start now doing the differential, partial differentiation we substitute it in our what? In our equation. So let me call this equation maybe A, okay? So if I do del u del x, this is equal to x prime. If I go ahead and say del 2u del x squared, this becomes, this is actually, we in partial differentiation, we vary only that variable and then we keep the other variable a constant. So this is going to be x prime times t, and this is going to be x double prime times t. So that is one. Then we look at the other side of del u del t. So del u del t is going to be, we are differentiating t with respect to t and keeping x a constant. Therefore, we'll have x t prime. So what does that mean? If I consider this one and that one being b. So what I'm going to do, I'm going to substitute b in A. Our A is this equation, okay, that forms the heat conduction, a partial differential equation, and therefore this is going to happen like this. So I will have x double prime times t. This is going to equal to 1 out of c squared, then x t prime. So if I do separation of variables, separating variables, what does this mean? This means that I'm going to have x double prime divided by x. This is equal to 1 out of c squared, then t prime divided by t. But I will say let x double prime divided by x is equal to 1 out of c squared, t prime divided by t equal to, for example, I'll say this is equal to nu, and what is going to happen is that I'm going to do something like this. I will have, first of all, to assume, I'm going to make an assumption here. So we are saying that x is a function of x only and t is a function of t only. So this, since this side I'm going to be having only x and this side I have only t, and remember c is a constant, then obviously nu is going to be a constant. So nu is a constant. So if it is a constant, then I will have x double prime minus x nu equivalent to 0. So, and obviously I will have t prime, okay, t prime out of t equivalent to c squared nu. But for us to simplify this problem, I know if you try, the fact that if you say, for example, let nu is equal to p squared, and then you substitute it in here, you are going to get solutions where p squared is greater than 0 and p squared is equal to 0. You'll find that when you substitute in here, and since you have second order differential equation and first order differential equation, what is going to result, for example, here, you will have a non-oscillatory solution. So since you have no non-oscillatory solutions, then we will disregard. So p squared greater than 0 and p squared is equal to 0 have been disregarded. You try it in your time and see what you'll have. You'll have non-oscillatory solutions, and remember here we are interested in oscillatory solution. So what is going to happen? I will take p squared less than 0. So if p squared is less than 0, what is going to happen? I will have x double prime. Therefore, I will have x double prime plus p squared, then x, this is equal to 0. So if I recall how to solve second order differential equations, I am going to create what we call an auxiliary equation. So an auxiliary equation, I can have m squared plus p squared. This being 0, then m will be equal to plus or minus jp. So this becomes a complex number, and therefore we introduce in our jp. So what does that mean? That the solution becomes a cos px plus b sine px. And that becomes one of our solutions. Then also, remember we have t prime divided by t equivalent to negative p squared. So we might, of course, we are going to cross multiply by this c, 1 out of c squared. So what is this going to happen? What is going to happen? We'll have t prime divided by t is equal to negative p squared c squared. So if I introduce integration, what does that mean? This is obviously equivalent to dt divided by, dt by, with respect to t, then divided by t, this is equal to negative p squared c squared. This is how it looks like. So if I do integration both sides, therefore I will have dt by t. This is going to be negative p squared c squared dt. Then I integrate also. So this is going to give me natural logarithm of t is equal to, I will have, for example, negative p squared c squared t plus c. Let me call it c1 to avoid confusion with this c I have here. So what does this mean? My t is therefore equal to, I introduce exponential, so negative p squared c squared t. Then remember I have a c1 here, so you'll have e to power c1. But also e to power c1 is a constant, so I just call it any constant, for example k. And so t is going to have a solution equivalent to k e or exponential of negative p squared c squared times t. Therefore, the general solution will become u x of t will equal to, I will have a cos px plus b sine px. Then I multiply everything by k exponential. Let me say this is k. This is going to be k exponential of negative p squared c squared t. So from here, I need to apply boundary conditions. I have u x t is equal to a cos px plus b sine px, and we are multiplying it by k exponential of negative p squared c squared t. So boundary conditions, the boundary conditions we are saying at we have u 0 of t is equal to 0 and is equal to u of a t. In other words, we are saying the temperatures are equal to 0 at x is equal to 0, and that is at the beginning of the bar and also at the end of the bar. So these temperatures have been fixed at 0, and therefore that's why we are saying this is equal to 0. So what I'm going to do, I'm going to apply a 0 here so that I will have a 0 equivalent to, if I put in a 0 here, I will have a plus 0. Then I will have k exponential, I will have k exponential of negative p squared c squared t. So we have to remember that I have now a k p squared c squared t is equal to 0. So now what we can say, you see here, this, okay. So maybe before that, let me first multiply this here, this k inside the brackets here, so that we remove it for good. Let's first remove it because this k, b, and a are all constants. So if I say a times k, I mean p is equal to ak, then bk is equal to 2, then I'll have u x t equivalent to, I'll have p cos px plus 2 sine px, then we're multiplying by exponential of negative p squared c squared t. So let's put in 0, so x is equal to 0 and x is equal to l, giving us u of all this equivalent to 0. So what does that mean? If I put in 0, I have 0 is equal to p, because a cos of 0 is equal to 1, so I'll have p, then plus a sine of 0 is a 0, so plus 0 times exponential of negative p squared c squared t. So I'll have p exponential of negative p squared c squared t is equal to 0. What we have to know that exponential of negative p squared c squared t cannot equal to 0, because we said whatever is here, if you have u of 0, t is equal to 0 or is equal to u L of t, this is true for all values. For all values of t, 0 between x and L. So that gives you no option of saying that exponential of negative p squared c squared t is equal to 0. So that means it gives you an option of saying that this p can equal to 0. So if p is equal to 0, then this is going to happen. U x of t is therefore going to be 2 sine px times exponential of negative p squared c squared t. Okay, so once we reach here, then we need to look at something again. We need to apply some other initial conditions. Actually, not initial conditions, but we now need to apply the second boundary condition. We need to apply now the fact that u of f of t is equal to 0. So this means x is going to be f. So that means I have 0 is equal to 2 sine p l, okay, exponential of negative p squared c squared t. We had earlier on said these two cannot be 0, because if it becomes 0, we cease to have no solution. Then also we said exponential of negative p squared c squared t cannot equal to 0. It leaves us with an option that sine p l will only be the component that will equal to 0. But for this to be 0, then p l must equal to n pi, whereby n is equal to 0, 1, 2, 3. These are integers. Because if you look at it, if we take sine of 0, you'll have 0. Sine of 180, you'll have 0. Sine of 360, you'll have 0. So everything is going to be giving here 0. So what does that mean? So PL equivalent to n pi gives you P equivalent to n pi divided by L. Yes, so meaning, therefore, that u x t will equal to what? This is going to be, if you are talking about a general solution, remember you'll have, if we are talking about n, there are going to be many They are going to be infinite or very many ux of t values, of course, due to n being at infinity. So therefore, ux of t will equal to, I'll now take the sum from n is equal to 1 up to infinity of 2n now, sine n pi x out of r times exponential of negative p squared c squared t. What does this now leave us with? We are going to now apply the remaining conditions, and that is actually apply the remaining conditions, that is initial conditions, because we want to now determine, these constants. So to determine these other ones, we can take them, the values can be there, they can be given, even L can be given, but we want to determine 2n. So, but remember, we can be given a condition that when t is equal to 0, then ux of 0 is equal to a function of x. So if that one happens, and this is true for all values, 0, between 0 and x, and of course the values of x between 0 and L. That's what we are saying. So what if that one holds true, then we will find that f of x is going to equal to the summation from n is equal to 1 up to infinity of 2n sine pi of x out of L. Because if when it is equal to 0, u of x0 is equal to f of x, it is true, because if we substitute in a 0 here, this reduces to 1, and we shall remain with it. Then, from Fourier series, 2n is equal to 2 or twice times the mean value of f of x sine n pi out of L x, okay? And what is going to happen? This is obviously from 0 to n. So you know, if you have 2n being the coefficient of sine, a sine function is an odd function. Therefore, the 2n is actually related to bn that you always see in Fourier series equations. And therefore, for us to get it, therefore, we will use also, we will use the sine function. So 2 of n, therefore, is going to be 2 out of L, integrating from 0 to L, times f of x, then sine n pi of x out of L with respect to x. So the moment we get that function, therefore, then, of course, this function is always going to be given, and you can do the integration and get that 2n. So if you get 2n, therefore, ux of t is going to be 2 out of L times the summation from n is equal to 1 up to infinity. Then we are multiplying this function here, integral from 0 to L f of x, then sine n pi of x out of L. This is here like this, and then we are going to create a curly bracket here. Then remember, this is 2n, so we are multiplying it by sine. This is going to be now multiplying it by sine n pi x out of n. Remember this we had then here is going to be exponential of negative p squared c squared t, and we cross this. So u of t is going to be 2 out of n summation of n from n is equal to 1 up to infinity of, now we create a smaller bracket, we are integrating from 0 to 1 f of sine n pi of x out of l. Then we cross this, we add sine n pi x out of l exponential of negative p squared c squared t, and that will be the solution for the heat distribution. So ladies and gentlemen, this is how analytically we can do the solution of this one-dimension heat equation using partial differential equations, of course, and using a method of separation of variables. In the next other discussions, we'll be looking at how we can do the coding of this in Python or in MATLAB so that we are able to visualize the solution numerically on a computer. Thank you. Thank you.